Hello everyone, my name is Shuhan. Today my topic is towards human-AI collaboration system for the detection of invasive ductal carcinoma in histopathology images. Today's presentation will be divided into following sections: background, research questions and objectives, proposed methods, results, and the last one is a conclusion. According to research, breast cancer is the second leading cause of death among women, with IDC accounting for 75% of all breast cancer diagnoses. Studies have shown that early diagnosis can significantly improve survival rate. This makes accuracy of early IDC diagnosis very important. But checking these images is a complex and time-consuming process which can sometimes delay treatment. Artificial intelligence effectively address this issue, especially with deep learning models like CNN, which have proved superior performance in automatically extracting features, thereby improving the efficiency and accuracy of breast cancer diagnosis. However, the quality of medical decisions depends not only on the capabilities of AI, but also on the effective interaction between AI and medical experts. To tackle this challenge, I implement a human-in-the-loop system in deep learning. This system first diagnoses and provides results through a high-performance CNN model. This is feedback from the AI to human. Then human experts make professional judgments on the results and relabel the misclassified images with the correct labels and add them to training data. This is feedback from human to AI. Finally, the model will be retrained. The study shows that human-AI collaborations outperforms using the model alone and can provide strong support for further AI diagnostic system. The aim of the study is to develop a human-AI collaboration system that enhances the accuracy and efficiency of human experts in diagnosing breast cancer, while human feedback will be used to optimize the model. This can be broken down into the following objectives: algorithm development, performance evaluation, and establishing a human-in-the-loop system. The research questions are: what are the steps and functions of data pre-processing? What are the metrics for evaluating the model? And what's the method for enabling human-in-the-loop? The study used a public dataset from Kango. 198,738 patches were identified as IDC negative, while 78,786 patches were identified as IDC positive. Each size 50 by 50 pixels were extracted at a magnification of 40. In deep learning, data quality determines model performance, so data processing is a crucial step. First, an imbalanced data set can lead to model to prediction bias, so I selected 7,000 samples from negative and positive cases. Next, normalization was performed to help the model converge faster. Normalization can be accomplished by multiplying the pixel values by 1 over 255. Then, data augment was applied to increase data diversity and reduce overfitting. This was achieved by generating two new images from the original image through rotation, translation, shearing, and scaling. Finally, data splitting was conducted, with 70% of data used for training and 30% for testing. Regarding the model, the study proposed a transfer learning model based on EfficientNet V2S. Compared to other models, EfficientNet V2S is a lightweight framework that focuses on optimizing training speed and efficiency while improving model accuracy. The core of the transfer learning lies in using parameters and weights trained on other large-scale datasets as a starting point for new tasks. In this study, the model was pre-trained on the ImageNet dataset. Using the learned outcomes from it, ImageNet is a large-scale dataset containing millions of well-labeled images across various categories. By pre-training on ImageNet, the model can learn rich and general features, enabling it to adapt more quickly and enhance performance when facing new tasks. The figure on the right shows the structure of the entire model, consisting of base model, bench normalization, test layers, dropout, and output layers. This method not only enhances the model's generation capability, but also demonstrates higher efficiency and performance in handling complex image classification tasks. Next, let's look at the design of a human-AI interaction. First, I made a page as shown on the left, which is used to input images and predict results. As shown on the right in the flowchart, the model is first trained with the initial dataset. When the image is input, the system uses the initial model to make a prediction. The result is fed back to the user, and if the human express judgment the result is wrong, the image will be correctly labeled and added to the training set to retrain the model. This is the human in the loop. The core of the human in the loop approach proposed in this study is to continuously train the model on misclassified samples. Human intervention creates the diversity of datasets, allowing the model to learn more previously unseen features. To validate the effectiveness of this method, as shown in the figure, I selected 20 negative and 20 positive misclassified samples. Make a total of 40 samples. After adding them to the training set and retraining the model, I tested these 40 samples again to observe if the accuracy improved. I did 4 sets of experiments and the images are different every set. And then we're going to see the results. As shown as the figure below, I used the confusion matrix to calculate the performance metrics, including accuracy, sensitivity, specificity, precision, and the F1 score. We can see the results are superior. Additionally, I plotted curve graph with accuracy and loss values to observe the trend of model performance over epochs. It can be seen that the model performs well in terms of accuracy and loss on both training and test sets, with no signs of overfitting. Compared the results with other studies, as shown in the table, higher metrics indicates better performance. The proposed method outperforms other studies in terms of performance. Here are the results for human in the loop before and after. I did 4 sets of experiments. Before the experiment, the accuracy rate was 0 because we were selecting samples from misclassified data. After the experiment, we can see that the model can correctly classify most of previously wrong images, which show that the method is effective. Although the model in the experiment shows excellent performance, but there are still some shortcomings. First, the form of data is too simple. Second, the model may not be up to date and therefore may not have the best performance. Finally, the human-AI interaction process in the study is somewhat simple, so the results are less convincing. Therefore, in the future plan, magnification and size can be tried first and then compared, because studies have pointed out that different magnification and size have a great impact on the performance. Then it is proved that EfficientNet V2L performs better, so we can try to change the model in the future. In addition, for better human-AI interaction, it is necessary to improve the explainability of AI, and using some prediction maps can better help humans improve the algorithm. Finally, Different human-in-the-loop design can be tried, such as active learning, which can provide better learning strategies and better optimization of the model. In summary, this study not only showed the excellent model performance but also is a good attempt to human-in-the-loop, hoping to provide strong support for future AI diagnoses. Here are the references. Thank you very much.